fields. What can we say about that? Well, let's start with some applications. You can have a large electromagnet, which is a coil, and a large magnetic field through the center of the coil. And if you put a magnetic material in that, you can enhance that as well. So that's definitely a controllable device where you can come up with a large magnetic field upon demand. Motors, meters, speakers, all operating on the principle of induction and associating the mechanical torque with the induction of a magnetic field. These devices, many of them designed originally by Tesla himself, and many of them, those original designs still work beautifully. Recording media. If you were to record something, you could use a magnetic field as a tip to orient the domains in a media such that when you come back, that oriented domains can help reproduce that information through another receiving magnetic tip. And so if you record media in terms of digital, either ones or zeros, then you can record all sorts of video and sound in this manner. Same thing with computer memory. You can record data bits in the same way as writing it down on electric magnetic material and then reproducing that by bringing a magnetic tip near that material later on. Magnetic resonance imaging, MRI. If you put the human body in a very large magnet, you will orient the domains of magnetic field within the body in one particular direction. Then if you come in with a transverse alternating magnetic field, much smaller than the first one, you can oscillate those domains in a particular way, and then they will radiate a signal that can be picked up as an image of the body. So it's a non-intrusive way, a non-surgical way of going inside the body and seeing what's there. Techniques in MRI have advanced considerably in the last 10 years, and they will continue to advance considerably in the next 10 years. Magnetism is related to electricity. They're interrelated, they're intertwined, they cannot be separated. If you change a magnetic field, you'll get an electric field. If you change an electric field, you'll get a magnetic field. In fact, if you continue in physics through physics 3, in relativity, if you choose the right reference frame, you can transform an electromagnetic field into purely an electric field or purely a magnetic field. They are intertwined, they are interrelated. Here's a magnet with a north and south pole, and here's another magnet with a north and south pole. Like poles repel each other, and unlike poles attract. As we look at this, any particular magnet, we have magnetic field lines emanating from the north pole and terminating on the south pole. Actually, the field lines actually go all the way through, so they're really closed loops. But they look like in this device that they emanate from the north pole and terminate on the south pole. So if I had these two magnets close together like this, we would have magnetic field lines emanating from this north pole over here and then terminating over on the south pole of this other magnet, causing the attraction between the two. Every magnet has a north and south pole. There are no known monopoles. So if I were to come in with a very, very sharp scissors and cut one of these magnets in two, what would happen? Well, I would end up with two magnets. So if I cut this down the center here, then I'll end up with a north pole just to the right and a south pole just to the left. I'll have myself two smaller magnets, each with a north and south pole. If I continue to do that, cut these magnets in half, I will end up with smaller and smaller pairs of magnets, each with a north and south pole. I will never get to the point where I can isolate one pole by itself. For every north pole, there is a south pole. It's really a consequence of the fact that these truly are closed loops, and hence even if I cut the magnets, I'm going to end up with closed loops no matter what. That being said, there's recent scientific inquiry into temperatures really, really cold, where scientists have claimed to have isolated a magnetic monopole. But that has yet to be confirmed, and so we'll leave it at that. The Earth is one big magnet. And if you had a compass, which has a magnetic needle, the north pole of your needle would point towards the south magnetic pole of the Earth, which is actually located close to the north geographic pole, and vice versa. So the magnetic pole of the Earth, south magnetic pole, is up to the north, and the north magnetic pole is down to the south. At least for now. Every couple million years, the poles of the Earth reverse polarity. No one really knows why. The source of the Earth's magnetism is swirling molten material in the Earth's outer core, which includes magnetic material and metal material, and swirling around, creating a dynamo effect, creating this magnetic field. So every once in a while, though, these poles reverse, and we're not really sure what's going to happen when that does happen. We might be overdue right now. It might happen tomorrow. We're not sure how that would disrupt the Earth if that were to happen. In Alabama, the declination, at least at the point where I made this slide, is about 5 degrees east. So if you had a compass in Alabama, you could be about 5 degrees off from true north. Of course, I've heard other reports where the declination is right on. To be sure, I would just use your iPhone GPS, and then you'd be exactly right. The magnetic field, here's a little bit of history. Hans Christian Ørsted in 1777-1851 found that an electric current in a wire deflected a nearby compass needle. In other words, if you took a wire like this and you had a compass around it, you would find that as you move that compass around this wire carrying a current, that the needle would deflect in such a way as it would indicate that there was actually a circular magnetic field going around this wire current. How interesting is that? More on that a little bit later. Andre Ampere suggested that molecular current loops are responsible for all magnetic phenomena. And even though the atom was not proposed yet, he was correct. As you go down into the atom, where electrons are moving around, electric charges are moving, hence changing their electric field, that is the ultimate source on that scale of magnetic fields. Joseph Henry demonstrated that a changing magnetic field produces an electric field, and James Clerk Maxwell theoretically showed that a changing electric field gives rise to a magnetic field. What does all this mean? Well, it just kind of reaffirms what I was just saying on the previous slide, that either experimentally or theoretically, if you change a magnetic field, you get an electric field, which is really the source of our power generation techniques. Or if you change an electric field, you get a magnetic field. They're intertwined. Here are some experimental observations. A stationary charged particle does not interact with a static magnetic field. So if it's not moving, nothing will happen. But when moving through a magnetic field, a charged particle will then experience a force. The force will be maximum when the particle moves perpendicular to the field, and minimum, or zero, when the particle actually moves along the field lines, either parallel or anti-parallel to the magnetic field lines. The force will alter the direction of motion of the particle but not its speed, because the force will always be perpendicular to the velocity of the particle. The force is proportional to the magnitudes of the velocity and the magnetic field, respectively, and we represent magnetic field with the symbol B. YB, I'm not sure. I mean, we're using M already for mass, and B is kind of like an M turned on its side with a bar on it. So maybe that's why we use B for magnetic field. That's my explanation, and I'm sticking to it. Mathematically, we summarize all this as a cross product. The force on a charge moving in a magnetic field is equal to the charge, which is a scalar value, times the velocity crossed with the magnetic field. The magnitude of this force is going to be the magnitude of the charge, magnitude of the velocity, magnitude of the field, magnetic field, times the sine of the angle between the two vectors, the velocity and the magnetic field. And the direction of this force is given by the right-hand rule. Right-hand rule would be for a cross product. You point your fingers in the direction of the first vector, in this case velocity. Close your hand in the shortest angle possible to the direction of the second vector, which is the magnetic field, and then your thumb would point in the direction of the cross product, which will make it perpendicular to the plane formed by the first two vectors. Velocity and magnetic field will form a plane, and the force will be perpendicular to that plane. If the charge is negative, you would do the cross product, and then you would flip it 180 degrees to get the direction of the force for a negative charge. So it looks like this. I said, point your fingers in the direction of the first vector, the velocity. So the hand as close as I can draw it using a cursor. Close it on the magnetic field, and then your thumb points in the direction of the force if it were a positive charge. Comparison of electric and magnetic fields. For electric field, if you have a charge, the force is going to be in the same direction as that field if it were a positive charge, and 180 degrees anti-parallel if it were a negative charge. So the force would be parallel or anti-parallel to the field, but for a magnetic force, it is going to be perpendicular to the field. So the force will be perpendicular to the field, and for that matter, perpendicular to the direction of the velocity. So it will change the velocity. It will be an acceleration in the sense that it's changing the direction of the velocity, but not its magnitude. For an electric field, the force is independent of the velocity. For a magnetic field, it only exists if the velocity exists, and it's actually proportional to the value of the velocity. For an electric field, it changes the speed and kinetic energy of the particle because it's acting in the same direction that the particle is moving. For a magnetic field, it does not affect the speed because it's always perpendicular to the direction that the particle is moving, and hence it can't change the kinetic energy of the particle either because it can't change the magnitude of the speed. It can only change its direction. So here's an example. A duck flying due north at 15 meters per second passes over Atlanta, where the Earth's magnetic field is 5 times 10 to the minus 5 Tesla, in a direction 60 degrees below the horizontal line running north and south. If the duck has a net positive charge of 0.4 microcoulombs, what is the magnetic force acting on it? So here we're looking at a side view of Earth. We can see the Florida Peninsula. We can see the Yucatan Peninsula. The star is Atlanta. So the Earth's magnetic field is going from south to north geographically, and hence if you had the Earth right there, you would see that the magnetic field is parallel to the surface of the Earth normally. But in this case, we're told that it's going down into the Earth at an angle of 60 degrees. It might be some kind of magnetic vortex there near the Bermuda Triangle. So you are a bird flying north. Here's a bird flying north, as best as I can draw it using a cursor. It's a rather sickly bird, sorry to say. But he's flying north, and there's a magnetic field on him, and we want to find what is the force, the magnitude and direction of this force. Well, the magnitude would be equal to the charge times the velocity times the field times the sine of the angle between those two vectors, the velocity and the magnetic field. We have a charge of 0.04 microcoulombs moving at 15 meters per second. Earth's magnetic field, 5 times 10 minus 5 Tesla, and the angle between those two vectors is 60 degrees. So we have sine of 60 giving us a force of 2.6 times 10 to the minus 11 newtons. So this duck will feel a force of 2.6 times 10 to the minus 11 newtons. What's the direction? Well, if I point in the direction of the velocity and I close on the direction of the magnetic field, I'm pointing into the page as you're looking at it, and that would be west as far as we're looking at the side view of the Earth. So this duck is going to feel a little bit of a force to the west. Some scientists have surmised that this is how ducks know, or other birds know, that they are flying north, because they feel this little bit of force one way or the other. It's too small of a force, and it's more likely that the birds react to the position of the sun. The sun is more south and than in the northern hemisphere, so they probably just react to that instead of this really tiny force. Alright, so we have one cross product equation. When we're done here, we're going to have 3 cross product equations. Consider this. We have a wire carrying charge, and the wire is in a magnetic field. So there is going to be a force on each of the charges in that wire. If we accumulate all the forces on each charge and apply it to the wire, we would get the force on a current carrying conductor or a wire. And that's what we're going to look at. Consider a volume of length L and cross-sectional area A. The number of charge carriers in that volume will equal the number of carriers per volume for that material, be it copper, silver, gold, whatever, times the volume of that segment, which is cross-sectional area times L. If we multiply the number of carriers by the charge or the force on each individual carrier, we would get the total force on the charge carriers in that wire. And hence, that would be the force on that segment of wire. Now note from chapter 27 that the current is equal to the number of carriers per volume N times the cross-sectional area A times the charge per carrier times the drift velocity. So if I make this substitution in to this equation up here, I get that the force on a segment of wire of length L is equal to the current times the length times the magnetic field times the sine of the angle between the current direction and the magnetic field direction. So that is the force on a current carrying wire. It really is actually a cross product. The force on a current carrying wire is equal to the current times the L vector. The L vector is a vector that represents the length of wire, and the direction of that vector is actually in the direction of the current, crossed with the magnetic field. And direction again can be found by the right hand rule. If you were to point your fingers in the direction of the current, close your hand in the direction of the magnetic field, your thumb will point in the direction of the force on the wire. In this case, we have a definite direction for the current, so this will always be the force. We're not going to be thinking of positive or negative current. We choose the current direction and do IL cross B, and we have the force. Let's try this out. A wire carries a current of 22 amps from east to west. Assume that at this location the magnetic field of the Earth is horizontal and directed from south to north, and that it has a magnitude of 0.4 times 10 to the minus 4 Tesla. Find the magnetic force on a 36 meter length of wire. How does the force change if the current runs west to east? So we're looking at this wire from a bird's eye view, looking down at the wire from above as we're looking down to the Earth. And the wire is carrying a current east to west. Earth's magnetic field is going, at least geographically, from south to north. So we're going to have a 90-degree angle between the two. The magnitude of the force will equal ILB sine theta, where I is the current, 22 amps. The length of the wire is 36 meters. Earth's magnetic field is 0.5 times 10 minus 4 Tesla. And, as we said, the angle between the current and the magnetic field in this case is a right angle, which is 90 degrees. Sine of 90 is 1. So this is 4 times 10 minus 2 newtons. And if I point, I'm going to see it from the way you're looking at it. If I point in the direction of the current, imagine how you're looking at it. This would be directed into the Earth. Well, I think you're looking at this. The current's going this way, field's going this way. So if I point in the direction of the current, close on the field, I'm going into the page, into the Earth. So if this were a horizontal wire above the Earth, surface of the Earth, carrying it from east to west, this wire would be pushed downward. How would this change if it were carrying a current from west to east? Well, it would be pushed upward. So if the wire were light enough in terms of weight per length, it's possible that it could levitate due to this magnetic force, or actually even start moving upward due to this magnetic force. Brings in thoughts of Edley Scalnan of Coral Castle, where the legend says he built this coral castle down near Miami in Florida. And I'm not going to give you the full story. You should look it up. It's really interesting. But the legend says that he found the secret for of the Egyptians for building pyramids. He built this coral castle. He was a 100-pound guy, had a rudimentary pulley system, did not have many tools, and he was able to somehow move a multi-ton, up to 60-ton boulders and quarry boulders of coral, and built this coral castle. How did he do that? The legend says that he had discovered the secret of magnetic currents and was able to levitate these objects and move them from place to place. Look up the story; it's great. Google it, Coral Castle, and I actually think I know the real solution to how he solved this, and maybe I'll reveal that in a later lecture. But it's interesting. He wrote 3 papers, magnetic currents. You might be able to find that on the internet as well. I've read those papers and can't make any sense of it. He was not a scientific person as far as having a language, scientific language, or studies in science. So it's hard to understand what he was saying in his papers. But maybe you can decipher it. Here's another problem. A wire carries a steady current of 2.4 amps. A straight section of the wire is 0.75 meters long, lies along the x-axis. Magnetic field is 1.6 K Tesla. K is in this font, that should be a unit vector. If the current is in the positive x direction, what is the magnetic force on the section of wire? Well, the force is a cross product, IL cross B, and that would be equal to the current, 2.4 amps, times the length of wire, 0.75 meters in the I direction, crossed with the magnetic field, 1.6 Tesla, in the K direction. I cross K actually is, I cross K is actually negative J. So the force is going to be down in the Y direction, And it's going to be equal to negative 2.4 times 0.75 times 1.6, or negative 2.88 J newtons. So that's the other way that you could figure out the force of a current carrying wire in a magnetic field. Here's the application, a speaker. Consider this. We have a coil around a paper cone, around a paper cylinder here, and it's basically on a magnet. We have a north pole here, south pole down below, south pole up top. And we run a wire in this coil, and we're looking at the cross section of that coil right now. And you can see that the current is running into the page on the bottom and out of the page towards you on the top. So it's going like this. Now if I look at the wires on the top with the current coming out towards you and the field going upward, I would have a force going to the left, forcing this cone to the left due to the force on the wire segments on top. And if I look at the bottom with the current going into the page and the field going down, if I were to point in that direction and go down, I again will have a force in the same direction going to your left. Hence, this whole device, this whole paper cone, will be forced to the left as I run a current through this coil. If I run a current in the opposite direction, this cone will be forced to the right. So if I were to alternate this current between one direction and then the next direction, this cone will move back and forth. In other words, if I feed the current an AC current that's alternating between positive and negative with a definite frequency, then mechanically that electrical frequency would be transferred into mechanical movement with the same frequency as the electrical signal. And hence, this cone would move back and forth, creating a pressure wave with the same frequency as the frequency of the signal going in to the wire, the current. So that frequency would be transferred as a pressure wave. That pressure wave would travel through the air, and then when it hit your eardrum, it would move your eardrum back and forth, and your eardrum would have the same frequency as that pressure wave. Hence, you would interpret that as sound. So an electrical signal with a particular frequency is transferred into a mechanical signal. It's transferred into a pressure wave, transferred to your ear, transferred as you interpret it in your brain as sound. And that's how any kind of speaker of this nature works. Consider this. We have a loop of current and we put it in a magnetic field. What's going to happen? Well, if I look at the wire segments on the top and bottom of this loop, they're either anti-parallel or parallel. And we know that if we have a magnetic field, if the angle between the current direction and the magnetic field is 0 or 180 degrees, then we'll have no force because it's sine of 0 or sine of 180 is 0. But if I look at the right segment here, there will be a force on it. It'll be equal to ILB sine theta, where we have a current I. Our L is going to be this length Y, and B will be the magnitude of the magnetic field, and the angle between the two is a 90-degree angle, so it will be sine of 90 or 1, and hence that force will be I times Y times B. The direction of it, as that current is going up and the magnetic field is going to the right, that direction will be into the page. If I look on the left-hand side of this loop, I'm going to have a current going down. I'm going to have another force, which will also be IYB sine theta, not IXB on this, but IYB sine theta. And the direction of that force, as that current's going down and the field's going to the right, will be out of the page towards you. So on either side of this coil, we're going to feel a couple of forces in opposite directions, causing this loop to start turning like this. So into the page on the right, out of the page on the left, and the loop turns as a result. well, then we have a torque on it. Because if it's turning, there's a force with a moment arm, two forces actually with two moment arms, causing a net torque on this coil. And this is the basic principle behind a motor, using induction to create a torque, a mechanical torque, and basically translating electrical energy into mechanical energy. Here's a top view. We have one force going into the page with a moment arm of x divided by 2, the other force going out of the page with a moment arm of x divided by 2. So we have those two torques, add them together, will give us our net torque. So F x divided by 2 plus F x divided by 2, IYB x divided by 2 plus IYB x divided by 2 is the magnetic field B times the current I times x times y. X is one dimension of the rectangle, y is the other dimension of the rectangle. The area of the rectangle is x times y, so this x times y is indeed the area of that rectangle. So we can write this torque then. Our maximum torque is being equal to the field times the current times the area of the loop. We did this for a rectangular loop, but we could have done this using calculus for any shaped loop. That the maximum torque would be equal to the field times the current times the area enclosed by the wire loop. We can also define what we call an area vector associated with this area. It is a vector that is perpendicular to the plane of the loop, and it, if we use the right-hand rule, if we curl our fingers in the direction of the current in the loop, our thumb would point in the direction of the area vector. So in this case, for this loop, the area vector is coming out of the page towards you, and as the field is going in the positive x direction, there's going to be a 90-degree angle between those two vectors. So curling your hand counterclockwise produces this area vector. It's one of those many right-hand rules we're going to define before we're done. With the area defined this way, the torque becomes field times current times area vector, at least the magnitude of the area, times the sine of the angle between the area vector and the magnetic field. So in cross product form, it is the current times the area vector crossed with the magnetic field, A cross B. Which, if we define what we call a magnetic moment, which is the current times the area vector, hence the magnetic moment is going to have the same direction as the area vector and multiplied by the current, then we say that the torque on this loop is equal to the magnetic moment crossed with the magnetic field. If the coil has several turns, like n turns, it will be magnified by the number n crossed with the magnetic field. We could do this easily by just taking a core and wrapping a wire in successive loops around a core, and every loop will actually have the current flowing in the same direction. So we'll have all these different loops adding ultimately to the torque, each loop adding the same amount to our net torque when we run a current through it. Let's try a problem. A circular wire loop has a radius of 50 centimeters, a current of 2 amps. A magnetic field of 0.5 Tesla is oriented at an angle of 30 degrees to the loop as shown. Find the magnitude of the torque at this instant. Well, we need to find the area vector, the direction of it, and we have a current coming out of the page towards you, at least on top, and into the page away from you on the bottom. You're seeing a cross section of it. So it's coming around like this. If I were to curl my right hand fingers in the direction of this current, my area vector is pointing in the positive x direction. So that is the direction of the area vector. Hence, my torque is the field times the current times the area times the sine of the angle between the area vector and the magnetic field. And we only have one turn, so our N is 1. And this is 0.5 Tesla, 2 amps. The area of the coil is pi r squared. The radius is 0.5 meters squared. And the angle between the two vectors is 30 degrees, giving us a torque of 0.39 Newton meters. If I were to add 2 more loops to this, I simply would increase the torque by 2 more. So my total torque would be 3 times the amount that I had for one turn. 3 times 0.39, 1.2 Newton meters. So the total torque on a loop would be equal to N times I times A times B times the sine of theta, MEAB sine theta, or if you rearrange the letters, Bain sine theta. And that would be the total torque on a multi-looped coil. By the right-hand rule, the magnetic moment is in the direction of the magnetic of the area vector, and if we were to calculate the cross product between the area vector and the magnetic field, or the moment in the magnetic field, we would end up, pointing in the direction of X and closing on B. Our torque vector would actually be into the page. Now, you know from mechanics in physics 1 that if you have a rotation, clockwise rotation would have a torque vector going into the page, counterclockwise out of the page. So this whole loop here, by the torque vector right-hand rule, is going to represent a rotation of this thing moving clockwise. In other words, the magnetic moment is going to move toward the magnetic field. And if you didn't want to think about all these right-hand rules, because there's 3 of them involved here, we had to think of the area vector direction, we had to think about the cross product, and then we had to think about the torque rotational right-hand rule. If you didn't want to think about all 3 of those, what you could do in a problem like this is realize that if a coil has a magnetic moment and there's a magnetic field, the coil is going to want to align itself with the magnetic field in whatever way it can. So the magnetic moment's here, the magnetic field's here. It's going to move in order to align itself with the field, and hence the coil will turn in that direction. That's why you would use multi-phases in terms of running a current through this coil, so that you don't always just align it, you put it out of phase so it keeps on turning again and again. That concludes the 3 vector equations that you need to know for a charge moving in a magnetic field, a current, wire current in a magnetic field, or the torque on a loop of current in a magnetic field.